Alright, welcome back everybody. Let's take a look at Unit A2, Standard Atmosphere. Standard Atmospheric Model, US, sometimes called US Standard Atmospheric Model. We already covered in fluid mechanics, at least the basic concept of that. You guys already know. So in Aerodynamics 1, we are going to revisit the basics of standard atmosphere. Now, the purpose of this unit is going to build a more accurate model than the model we already know from fluid mechanics. Okay, so these are the subjects we're going to cover in Unit A2. Number one, I'm going to define what is altitude. We have different kinds of altitude, so let's make sure if you're talking about altitude, what altitude you're talking about. Okay, then of course we are going to start from hydrostatic equation, and then we're going to model standard atmosphere based on two different kind of regions. One is gradient region, the other one is isothermal layer. So baseline is very, very similar to what we did in fluid mechanics, but pay attention to the difference that we are going to introduce you here. Okay, so let's take a look at page 1. Alright, so this is the page 1 of Unit A2 note. So this page describes you different types of altitudes. So let's just take a look at it. Now altitude comes with two different definitions. One of them is called absolute altitude. This is usually employed by spacecraft dynamics, attitude control. This is the distance measured from planet's core to the location of altitude. So this is called absolute altitude, H sub A. Okay, so this is usually employed by space mechanics people. Now this is aerodynamics class, so we're not going to use this one. So instead of using absolute altitude, we are going to employ geometric altitude, which is basically measured from the surface of the Earth, usually sea level. Then you're going to measure the distance to that location of altitude. This is called H sub G, geometric altitude. So in aerodynamics context, if someone says altitude 5,000 feet, that usually means that H sub G, geometric altitude, measured from the surface of Earth, usually sea level, is 5,000 feet. Okay? Obviously, the difference between H and HG is the radius of Earth, which is given here. This is the value of radius of Earth. Okay. All right. So having said that, we are going to revisit the model we built in fluid mechanics, and then we are going to talk about difference we are going to incorporate within in aerodynamics model. So this is going to be standard atmospheric model. Difference from fluid mechanics. Remember, in fluid mechanics, you are first exposed to establish a standard atmospheric model. Okay. Now, in fluid mechanics, in order to simplify the analysis, okay, we assumed gravity is constant. Throughout the atmosphere. So this is a simplification necessary in fluid mechanics. However, gravity is not really constant. of course, gravity keeps changing. So as you increase your altitude, obviously the gravity keeps decreasing. Okay. So let's go back here once again. So right here, this is the gravity as a function of altitude. Okay. So this hg, like I said, this is a geometric altitude measured from sea level and to the location of altitude. This r is a radius of us. This g0 is a gravitational acceleration measured at sea level. So this is a standard sea level value. So gravity is no longer be standard sea level value as you increase this hg. Let me just write it down here. So first of all, g0, this is standard sea level value. We know these standard sea level value, 9.8 feet per second square or 32.2 feet per second square. So G0, standard sea level value. However, the gravity is a function of hg. Okay. Gravity, G, is a variable, not the constant, which depends a function of hg. So gravity is not constant, but rather gravity depends on hg. It just keeps changing. It just keeps decreasing as you increase hg. Okay? So somehow we want to incorporate this changing gravity into our analysis here, or into our model equation which we developed in standard atmospheric model. Okay? So that's what we are going to do here. So let's move on to the next page. Okay. So now obviously we are going to once again begin our model equation from hydrostatic equation. Remember hydrostatic equation from fluid mechanics. We are going to use the exact same equation developed in fluid mechanics. There's no difference. We are going to start from the same exact governing equation. Okay. So before we begin, hydrostatic equation. Do you remember hydrostatic equation from fluid mechanics? I hope so. dP dz is equal to minus gamma as a function of z. This is the hydrostatic equation from fluid mechanics. Keep that in mind. Z is height. Okay? So I don't want you to be confused, but in aerodynamics, we are going to use altitude h. hg, okay? So let's just use hg and rewrite the same equation. So this really means that dp dhg is equal to, gamma is rho times g, isn't it? So minus rho times g. G is a function of hg. That's the problem. That's it. So this is the same exact equation written in terms of aerodynamics notation of altitude hg instead of z, height. Okay? So it's the exact same thing. So this actually tells you what is dp is. dp is equal to minus rho times g. Keep in mind g is a function of hg, dhg. Is that right? The important thing is this guy. So this equation tells you that gravity is not the constant. Rather, function of hg. That's what this equation tells you. So that's exactly the same equation you see here. Okay? Here we go. This is a hydrostatic equation. Okay? Coming straight out from fluid mechanics. Okay? Now keep that in mind, this G. This G is not a constant, it just keeps changing. So that means you have a variable which depends on hg. And not to mention, this is density. Density within atmosphere is also a variable of hg. So this is a variable which depends on hg. This is also another variable depends on hg. So making this equation highly nonlinear ordinary differential equation. Okay, very nonlinear ordinary differential equation, which is not very good. You really cannot integrate this equation to come up with algebraic form of equation, which we did in fluid mechanics. Now in fluid mechanics, what we did was we assumed this is constant, then we can integrate both sides. That's what we did. Now we cannot do it because we want to incorporate the change in gravity here also. Problem. What can we do? So here is the solution. Okay, very, very important concept. Okay, so let's introduce something like a fictitious altitude. Fictitious altitude, what do you mean? Altitude definition we just basically make up. This is called geopotential altitude. Okay? Geopotential altitude, we are going to use h, lowercase h, to represent geopotential altitude. What is the geopotential altitude? Let's take a look at here. Okay. Geopotential altitude, h, is essentially a variable depending on hg. So hg is the actual altitude. This is actual distance measured from sea level to the location of altitude. So if it's 5,000 feet altitude, that means 5,000 feet distance measured from sea level to 5,000 feet location. However, this h is defined by hg as well as radius of Earth. So that means this is going to tell you the equivalent altitude if the gravity doesn't change. So let me just explain a little bit more detail. What's the meaning of geopotential altitude, which is kind of finicky? So this is the sea level, okay? This is 5,000 feet, for example. And then this is hg. Okay? So if somebody says altitude 5,000 feet, that literally means that the distance 5,000 feet measured from sea level to the location you call hg, right? However, throughout this 5,000 feet altitude, gravity keeps changing. Gravity is g0 at the sea level, but the gravity is less than g0 here at the 5,000 feet. So gravity is a function which keeps decreasing. Okay? Alright? So, suppose, hypothetically, if the gravity is g0 and then always g0, In other words, constant value of gravity starting from sea level value G0, which we know this is 9.8 meter per second square or 32.2 feet per second square. So this is the gravity at the sea level G0, which is hypothetically, if it's constant throughout, what is the equivalent altitude of this 5,000 feet? Okay, so that is called geopotential altitude. Equivalent. If G equal to G0 throughout. Okay. If the gravity changes from G0 to lower value G, if it's 5,000 feet based on that environment, suppose if hypothetically you create the environment of gravity is constant, Hg becomes H, and it's no longer be 5,000 feet. Equivalently, this is going to be a little bit less than 5,000 feet. Okay? So relationship between Hg and H can be given by H equal to, it's given in your note, R over R plus Hg multiplied by Hg. Okay? This is a relationship between geometric altitude against geopotential altitude. Where does that equation come from? It's coming from, obviously, from here. So gravity is a function of Hg. So suppose if the gravity is constant, can modify Hg based on that constant gravity. Yeah, that's called H, geopotential altitude. Okay. I gave you a handout. To derive this equation. Excuse me. I gave you a handout. That handout is deriving this equation coming all the way from the definition of gravity as a function of Hg. Okay? So please take a look at it and understand why this relationship is true. Okay? So anyway, great news about it is this H, as long as you use this H, geopotential altitude, you can assume gravity is constant. Yeah. Oh, that's good. Oh, it is such a convenient thing. So I can tell by employing H instead of Hg. You can rewrite the hydrostatic equation So remember, original hydrostatic equation was dP is equal to minus rho g, but this g is a function of hg times dHg. Okay? So this is the original hydrostatic equation, can be modified to dP is equal to minus rho times G0. This is a constant value, sea level, and then this is constant, dH. Oh, big difference between them. This equation, density is a function of hg, gravity is also a function of hg. So those two multiplied together makes this equation highly nonlinear ordinary differential equation. This one of them is constant. So this is constant, even though density still depends on h. Okay, one of them is constant. So we can integrate this equation. That's great. Okay. So, and keep in mind this is constant. Okay. G0 is 9.8 meter per second squared. 72.2 meter per second squared. Okay. So this is going to be the hydrostatic equation, which is essentially, well, the same thing we did in fluid mechanics. So the rest is the same thing. So I hope this is going to be a review. So this is a hydrostatic equation. In terms of H, geopotential altitude. Okay. So now we are going to move on to next page. Let's just take a look at standard atmospheric model that we are going to introduce you in aerodynamics 1. So this is a very similar thing we already looked at in fluid mechanics, but we do know the temperature distribution within the atmosphere. That's the starting point. So this is the pre-knowledge that we know based on the measurement. Oftentimes we do measure the temperature distribution in the atmosphere. Okay. There's one interesting example that Embry-Riddle is actually involved. Let's take a look at it. So one of the interesting projects that we oftentimes do is this is a project called Ascend. Okay. I think Embry-Riddle is doing this activity once a year, at least. So this project, they're using balloon, weather balloon. This is a pretty strong latex weather balloon. They are going to connect up with a payload. So a major component of this research project is design lots of different payloads. Payloads include repeater station of ham radio signals. Could be a GPS device to locate the position, or could be a thermocouple to determine temperature within atmosphere. Okay, so they get together. Also, oftentimes invite local high school students. They launch this payload attached to this balloon. Then this one goes up, goes really high up. This actually goes to the near space, really high altitude. And then if you go up and up and up and up, atmospheric pressure goes down. So as a result, this balloon gets bigger, and gets bigger, and gets bigger. And then eventually, somewhere very close to the space, really high altitude, it just pops. Then lose the lift. Then this payload, after this balloon pops, it comes down. It's just a free fall, okay? And then come back to the exact same location that you launched. No way. It's not going to happen. This is going to come back to Earth somewhere pretty bizarre. It could be right in the middle of desert, someone's backyard, right in the center of big lake. I don't know what it is, but you have to hunt down. That's the fun part, because this one is equipped with a GPS device, so you can kind of track down and recover this payload, then extract the data out. Okay. So, what is the meaning of such kind of research project? Well, one of the significant achievement I can say in terms of aerodynamics is, as the balloon slowly go up and go up and go up and gain altitude, you just keep measuring the temperature. Then you can plot it, and then this seems to be typical result of temperature distribution within atmosphere. So atmospheric pressure, well actually atmospheric temperature, in this case temperature, behaves like this. Starting from sea level to 11 kilometer altitude, temperature begins to decrease almost linear function. This is actually linear function with a slope A1, reaching to the really low temperature, Then from here to there, stays constant for a moment, and then begin to increase linearly, and reaching to this temperature, then stay constant for a moment, and begin to decrease, stay constant, begin to increase. So it's a series of either linear change of temperature and constant temperature. Linear change of temperature, constant temperature. Linear change, constant, linear change. It's a series of that going back and forth. Okay? Now in aero, we are only interested in this region, that region. This region is commonly called troposphere. Troposphere is the layer where, starting from sea level, temperature begins to decrease linearly and reach to this much temperature. And this is called stratosphere usually. The temperature stays constant throughout. Now, typical flight altitude of airplane is right here. Right here on the boundary between linear region and isothermal region. Okay? This is called gradient region. Gradient means temperature decrease linearly with the gradient. This is a gradient, okay? This is called isothermal layer because the temperature is constant. Alright? So, can we get the basic equation to handle this portion, which is gradient region equation? And do we have an equation which can handle this portion, which is isothermal equation? Yes, we can. We actually already know about those two equations from fluid mechanics. So we are going to go back again, derive those two equations, okay? By the way, keep that in mind. Let's go back here. Okay. So the very first thing in aerodynamics 1 model of standard atmospheric model is we are going to convert geometric altitude into geopotential altitude. That's the very first thing. Then use the geopotential altitude into your calculation inside. Then as the result comes up, those are the results corresponding to actually geometric altitude. Okay? So very first step, you have to convert using this equation, convert given geometric altitude hg into corresponding equivalent to geopotential altitude. Then use that altitude to come up with pressure, density, temperature. Okay? So that really means that this is a plot of temperature distribution. This is h, geopotential altitude. It's not the actual geometric. If the geometric altitude is 5,000 feet, first thing you need to do is to convert into geopotential, which is no longer be 5,000 feet. But use that value together with this to find out pressure and density corresponding to the known temperature. Okay? Let's be careful about that. So, let's move on to the next page. One more thing before we move on to next stage. Okay. Now, in aerodynamic model of atmospheric pressure, we always start from these values at the sea level. So this is something called standard sea level atmospheric values: pressure, density, temperature. We are going to always start from right here. Then suppose if this is an exam problem, I can easily create this problem. Think about that. I give you those values, standard sea level. Then question is, okay, find out pressure, density, and temperature at 100 kilometer altitude. What are you going to do? Well, it's going to be a nightmare. You're going to start from here, then you are going to pick up a first equation. First gradient region equation. Determine temperature, density, pressure right here. That's the first step. Second step, you are going to pick up isothermal equation using the values you just found. Determine the pressure, density, temperature here. That's second step. Third step, you're going to go back again to a gradient region equation. Using these values you just found in the previous step, you're going to determine pressure, temperature, density right here. That's the third step. Fourth step, you're going to pick up isothermal equation using those values you just found, find out the value here, temperature, density, temperature. That's the fifth step. Sixth, I guess you get the picture. You start from here, get this value using those values. You get this value using those values. You get this value using those values. You get this value using those values. Then you get this value using those. You get this value using those. Then you can determine. So it's going to be probably 5-6 pages of calculations. It's a nightmare problem, right? I can easily make that one happen. But that's probably not really fair. So suppose if you are given program saying determine 15 kilometer altitude pressure, temperature, density, what would you do? We are going to start from here, determine the value here, then using those values to determine 15 kilometers. Okay? We are going to take a look at the example problem like that. But first, let's develop an equation that actually covers this portion and those portions. Okay? So next page. I'm going to begin with gradient region standard equation, which is the algebraic form of equation. Okay? Gradient region. Gradient region is the region where, starting from the base location where you know temperature, pressure, density, starting from there, within this gradient region for given any altitude h, this is the geopotential, what is the value of temperature, pressure, density? Okay? So those are the three equations that actually can make it possible to do those kind of calculations. You can determine those out of these. Okay? So let's begin with it. So we are going to begin with hydrostatic equation. Okay, keep in mind, this is a hydrostatic equation in terms of geopotential altitude. So this G0 is constant, standard sea level value. Okay. We are going to divide both sides by equation of state. P equal to rho RT. I'm going to divide both sides of this equation by P equal to rho RT. So what do you have? dP over P is equal to minus rho G0 dH divided by rho RT. Now keep that in mind, P is equal to rho RT, so you can do this kind of thing. Left hand side you divide by P, right hand side you divide by rho RT. After all, P is equal to rho RT anyways. Okay? So what happens here, density goes away. You don't have to worry about the density anymore. Okay? So right hand side now becomes minus G0 over R dH over T. One thing quite significant. This G0 is a standard sea level value. This is constant. G0 equal to either 9.8 meter per second square or 32.2 feet per second square. This is just constant, so this is also constant. So G0 divided by R, this is a constant. Okay. All right. Now, what about the temperature? So this is the temperature. So for gradient region, T is a linear function So you can express temperature T is equal to whatever the base temperature T1 plus, this is how much temperature change happens linearly, multiplied by H minus H1. So this equation tells you that the temperature is a linear function within the gradient region. Okay? So let's go back, let's go to here. So what I'm saying is this is the equation of temperature. So temperature at the given altitude h is equal to whatever the known temperature here at the base of gradient region. This could be sea level. Okay? If so, you know the sea level value. Plus whatever the gradient multiplied by the altitude h minus h1. That's going to get you the temperature here because it's simply it's a linear function, right? Okay. So can we somehow incorporate this known function into here? Yes, we can. That's what we're going to do. Okay. So just erase here. All right. So let's define something called Raps rate A. So this is A. Raps rate A is essentially, let's take a look at this figure here. It's the slope of this linear line. That's called Raps rate. How much temperature increase or decrease happens as you increase your altitude within the linearly changing temperature region called gradient region. Okay? So let's define this. This really is essentially dt dh. In other words, how much temperature change happens for a given change of altitude. If this is linear, this is essentially change of temperature over change of altitude, right? Because it's linear. So this really means that between base and arbitrary location of altitude, T minus T1 over H minus H1. This is called Raps rate. Okay. So from here, you can say, what is dH equal to? dH is dt divided by A. Let's call this equation 1. Let's go back once again here. Going to previous page. So it looks like Raps rate for the first gradient region is some kind of minus value. That means this really tells you that the temperature decreases as you increase the altitude. This one is a positive value, right? So second gradient region, if you increase the altitude, the temperature increases. This one is minus. Again, the same here. This is plus. Same here. So here and here is a temperature increase, here and here a temperature decrease. One is negative, one is positive. Anyways. Okay. So this is a relationship between change of altitude to change of temperature through this constant value called Raps rate. Raps rate is given for each gradient region. Okay? Note. So A1 is given by minus 6.5 times 10 to the minus 3 Kelvin per meter from sea level to H equal 11 kilometers. Sea level means H equal to 0. Okay? So this Raps rate A depends on where you are. So from sea level to 11 kilometers, this is called troposphere. This is a constant value of Raps rate. Okay? So this really tells you that as you increase the altitude, the temperature decreases linearly. All right. So let's just come up with the gradient region equation. Okay. All right, so, okay, we stopped here. So recall, come up with this equation. We do know dP over P is equal to minus G0 over R dH over T. And let's combine this with equation 1. So that means let's plug in dH is equal to dt over A right here. So this actually gives you dP over P is equal to minus G0 AR dt. dt over T, sorry. dt over T. So I just substituted dH being dt over A. Here we go. So let's just take a close look at this equation. Left-hand side is all function pressure. Right-hand side is all function temperature. This thing is all constant. This is a constant gravity at sea level G0. This is gas constant. This is rupture rate. It's also constant within the gradient region. Right? So we can integrate this equation. All right. So let's do that. So I'm going to, okay, so before we integrate, right? Let's take a look at this figure. So how do we integrate? We are going to integrate from here to there, from base of the gradient region to some arbitrary height or altitude within the gradient region in a positive h direction, from here to there, from here to there. Right here, everything is known value, T1, P1, rho 1 at altitude h1. Right here, altitude h, those are unknowns. Let's be careful. So we are going to integrate from altitude h1, where the pressure is P1, we know that. At altitude h, pressure is P, which is unknown pressure. dP over P, right? Right-hand side, this whole thing is constant, goes outside of integral. So this is minus G0 AR, integral from altitude h1, where the temperature is T1, we know that value. At altitude h, temperature is T, unknown temperature, dt over T. Okay? Integral of inverse of pressure dP is natural log. So this is going to be natural log of P over P1, right? This is going to be minus G0 AR, natural log of T over T1. Let's move on a little bit more. Okay. Now we are going to take exponential for both, and then this one is going to be raised up to the power of exponential. No, this is going to be raised up to the power. So doing a little bit more math here, taking exponential for both sides, you're going to end up being P over P1 is equal to T over T1 to the power of this thing multiplied to natural log, which is power of minus G0 AR. Okay? So this really means that the pressure at altitude h, arbitrary altitude within the gradient region, can be given by P1. This is a known pressure at the base of the gradient region multiplied by temperature ratio T to T1. By the way, temperature T can be given by this equation. Okay? So these are both known value to the power of minus G0AR. Okay? Ooh, this is very, very nice algebraic form of equation that you can determine pressure out of given pressure at the base of gradient region. So obviously you can use this equation to find out pressure at the given altitude h. Okay? Now we can also apply P equal to rho RT to this equation. Let's do that. So this is going to be rho RT over rho 1 RT1 is equal to T over T1 to the power of minus G0A R. Gus constant is constant, cancels out. So this actually gives you rho over rho 1. Density ratio multiplied by T over T1 is equal to T over T1 to the power of G0AR. Okay? You can bring this to the right hand side to get density ratio rho 1 is equal to T1 to the power of minus G0AR plus 1. Okay? So this will multiply to the minus 1 here, so minus goes outside of the bracket, so minus outside of the bracket. So this concludes that density at the given altitude h can be given by density at the base altitude h1, which is known value, multiplied by the ratio of temperature to the power of G0AR plus 1. Okay? So this concludes the equation of gradient region, which is fairly simple deal. I hope this is just a review from your fluid mechanics. So those are the equations already given to you in the notes. Let's take a look at it. So those are the three equations that you need to figure out the temperature, density, pressure. So first of all, temperature is a linear function. So this is the first thing you are going to find out, the temperature right here, T. Okay? Then once you get the temperature T, you can use the temperature ratio to figure out the pressure and density at the given altitude h. Okay? So this is gradient region equation. And let's move on next page. Let's take a look at then isothermal layer equation, which is much easier than gradient region equation. So to do that, I'm going to leave here because it's the same. I'm going to start erasing this one down. Okay? All right. So once again, we are going to take a look at hydrostatic equation in terms of H, which is geopotential altitude. Then you divide both sides by P equal to rho T, then come up with that. Up to here is all the same. So now we are looking at isothermal layer. So as always, we are going to start our calculation at the base of the isothermal layer. If this is a stratosphere, you start from 11 kilometer value, which is obtained from sea level using gradient region equation. So those are the known values, T1, P1, rho 1. Start from here at the given altitude h, what is the temperature, pressure, density. The first thing which you know is, hey, temperature is constant, So temperature T is equal to temperature T1, isothermal. Very simple deal. Isothermal really means that the temperature at any location within is constant. Okay? So whatever the value at the base of this isothermal layer, the temperature remains constant. Okay. So that actually makes this equation much simpler because this T is also constant. Constant joins into here as a chunk of constants. So let me just write it down here. dP over P is equal to minus G0 RT dH. So this whole thing is constant now. This is constant now. Temperature is also constant. Okay. So I can integrate from pressure at the base is P1. Pressure at given altitude H is P. dP over P. This whole thing is constant, goes outside of integral. So this is minus G0 RT. Integral from altitude H1 to H dH. Oh, very simple integral. Left hand side is natural log of P over P1. Right hand side is minus G0 RT multiplied by H minus H1, right? Let's take an exponential for both. Well, I don't have to tell you. Let's take an exponential for both. Get rid of natural log. That means P over P1 is equal to, right hand side is exponential to the power of G0 times RT multiplied by H minus H1. That's it. Well, let's move a little bit more. So that means P is equal to P1 multiplied by exponential minus power of G0 RT times H minus H1. So those two are the equation of pressure relationship between P and P1. So you can use this equation, knowing that the temperature is constant, you can determine the pressure at the given altitude H within isothermal layer using the base value, which is known value. Okay? Well, we can do the same thing with P equal to rho RT. Plug into here. Rho RT over rho 1 RT1 once again is equal to exponential minus G0 RT H minus H1. We do know this is constant, cancels out. Now in this particular case, T equal to T1, right? So we can also cancel out this one. Oh, what do you mean by that? Well, that means density rho over density rho 1 is equal to the same equation. Same equation, huh? So in other words, rho is equal to rho 1 times exponential minus G0 T H minus H1. So those two are the equations we got. So let's go back. Take a look at the three equations we got. This is the first thing you realize. This is isothermal, temperature is constant. So whatever the temperature T1 is, at any altitude within this isothermal layer, temperature is always T1, it's constant value. Okay? Then those are the pressure and density, which is the exact same equation. So that means pressure ratio is equal to density ratio. Have you ever heard of that in the past in fluid mechanics? Oh yeah. In isothermal flow field, pressure ratio is also temperature. Pressure ratio is also density ratio. Density ratio is also pressure ratio. I hope you recall that. If If not, let me just write it down here. I guess sometimes very fundamental things need to be revisited. So from fluid mechanics, we know for isothermal flow of gas. If you take a ratio of pressure and density, this is going to be constant. Okay? What do you mean by that? Well, that means if you have a flow of gas, maybe within a pipe or something, and location 1 here, location 2 here, this is a pressure P1, density rho 1, this is a pressure P2, density rho 2, T1, T2. Now, isothermal means T1 equal to T2 equal to T. Temperature is constant. If so, you can say P1 over rho 1 is equal to P2 over rho 2 is equal to constant. Okay? This really means that the flip-flop of it, this really means that P1 over P2 is equal to rho 1 over rho 2 is also constant. So that means if you're looking at the pressure ratio between 2 points and the density ratio between 2 points, same thing. Okay? That's what you're talking about. Because it's, why is that? Because it's isothermal. You remember this? I hope you remember this kind of thing from fluid mechanics, you know. If you have no clue about what I'm talking about, there's no meaning why you're taking fluid mechanics, okay? So these are the things that I really want you to pick up from fluids. Very fundamental idea of isothermal conditions. All right. So now we have all the equations available for us. Let's just take a look at examples. Let's apply those equations to find out atmospheric pressure values under the standard model. Using standard atmospheric model. Let's do that. So let's move on to page 6. Let's take a look at example problem here. Calculate the standard atmosphere values of temperature, pressure, density at a geopotential altitude of 11 kilometers, starting from sea level value, of course. Keep that in mind. Very important. This is a really nice problem because this problem gives you geopotential altitude. Nobody usually gives you a geopotential value. Okay? Probably if I give you the similar kind of problem in exam, I'm going to restate this problem saying if the altitude, quote unquote, it really means that the geometric altitude, Hg, is 11 kilometers, or maybe 10 kilometers, whatever. What is the temperature, pressure, density at that altitude? So what do you mean by that? If altitude, naturally speaking, altitude is geometric altitude. If that is given, the first thing you need to do is convert it to geopotential. Okay? Then use that to determine temperature, pressure, density. Okay? Now obviously this is not the case. This is a nicer problem. The problem tells you geopotential altitude of 11 kilometers to begin with. Okay, let's be careful about that when you do your homework. All right. So we are going to start from sea level, okay? Sea level means that, geometrically speaking, this is 0. If Hg is 0, geopotential altitude is also 0. Keep that in mind. Let me just bring it up, the equation of geopotential altitude. Okay. This is the equation of geopotential altitude. H is equal to radius of us divided by radius of us plus hg multiplied by hg. So this is a conversion from given geometric altitude to geopotential altitude. Okay, if hg is 0, of course h is 0 also, right? Okay. So let's start from standard sea level property, which is usually given to you. Let's call this PS 1.01325 times 10 to 5 Newton per meter square, which is Pascal. Density of sea level 1.2250 kilograms cubic meters. Temperature of sea level 288.16 Kelvin. Let's go back a few pages. Okay. So those are the standard sea level value, which corresponds to those value based of the gradient region. Since we are talking about fast gradient region from sea level to 11 kilometer right here, so starting from those values, what are the temperature, pressure, density at 11 kilometer? That's what we are doing. Okay. Let's go back here. So we are going to essentially pick up the gradient region equation. So we are going to find out temperature at 11 kilometers, which is T1. By the way, this is T1. Okay. This is rho 1. This is P1. Okay. So T1 plus A lapse rate times H minus H1. So this H is 11 kilometer, this H1 is sea level 0. This A is A1. So let's plug in. T1 is, of course, sea level TS. So 288.16 Kelvin plus A is minus 6.5 Kelvin per meters, multiplied by 11,000 meter minus 0. You cannot use kilometers because this is meters. Okay, let's be careful. Plugging 11,000, not 11. Common mistake. So this actually gets you temperature at 11 kilometer is 216.66 Kelvin. Let's quick check the sanity here. So if you go back to page 3, temperature at 11 kilometer is 216.66 Kelvin, right? So make sure you get the right value. So this value stays constant from 11 to 25. All right? Good. Let's find out pressure. Pressure at 11 kilometer is pressure at sea level P1, which is this, and multiplied by temperature ratio T over T1 to the power of G0 over AO. Okay? P1 is that 1.01325 times 10 to 5 Newton per meter square. Temperature ratio T, we just found 216.66 Kelvin at 11 kilometers. T1 is this, 288.16 Kelvin to the power of minus G0 is 9.8 meter per second square. Lapse rate minus 6.5 Kelvin per meter. Gas constant 287 Joule per kilogram K. Let's not be lazy. I'm going to put the units. Kelvin per meter. No. Minus 6.5. No, I don't think so. Sorry about that. I forget. I found a mistake. Minus 6.5 times 10 to minus 3 Kelvin per meter. Sorry about that. Minus 6.5 times 10 to minus 3 Kelvin per meter. 287 Joule per kilogram K. don't forget 10 to the minus 3. It cannot be this high. So, if you pick up your calculator, put those numbers in. What do you get? You should get 2.2650 times 10 to the 4th Newton per meter squared. So this is the pressure at 11 kilometers. Similarly, the density. Density at 11 kilometers is equal to rho 1 times T over T1 to the power of minus G0AR plus 1. Okay? So rho 1 is this one, 1.2250 kilogram per cubic meters. Temperature ratio, once again, 216.66 K over 288.16 K Kelvin to the power of bracket 9.8 meter per second squared divided by minus 6.5 times 10 to minus 3 Kelvin per meter, 287 joule per kilogram K, plus 1. Okay. So, if you plug those numbers in, you are going to get the density, which is 0.36420 kilogram cubic meters. Okay? So those are the temperature, pressure, density at the 11 kilometer altitude, 11 kilometer geopotential altitude, which is right here. Okay? So the next step is, suppose if you want to find out temperature, pressure, density at the 15 kilometers, for example, how would you do that? You're going to start from those values in the isothermal equation to get that. So that is the next example. So, page 7. Let's take a look. So page 7. This is the coming from the previous example problem. Let's calculate the standard atmosphere values of temperature, pressure, density at the geopotential altitude of 20 kilometers. Okay, 20. So previous example problem, what we did was we started from sea level. We found the values right here, temperature, pressure, density. We know that. So let's use those values, apply isothermal equation from here to 20 kilometers to find out the values here. Okay. Let's do it. Okay, so let's find out. From previous example. We do know temperature at 11 kilometer is equal to 216.66 Kelvin. Pressure at 11 kilometer is 2.2650 times 10 to the 4th Newton per meter square Pascal. Density at 11 kilometer is 0.36420 kilogram per cubic meters. So those are the given condition at the base of this isothermal. So those are essentially now becomes T1. This is P1. This is rho 1. So those are the base of isothermal layer. Then we are going to apply isothermal equation. The easy one is temperature at 20 kilometer is essentially the same. Temperature is constant, so this is 216.66 Kelvin. Instant answer almost. Oh, it's so easy. Because temperature is constant, that's called isothermal layer. Now what about the pressure? Pressure at the 20 kilometers. This is going to be P1, which is that, exponential minus G0 over RT, H minus H1. So let's plug in. So P1 is 2.2650 times 10 to the 4th Newton per meter square. Exponential, this is a 9.8 meter per second square. Gas constant 287 joule per kilogram K. Temperature is 216.66 K constant. Multiplied by H is 20,000 meter minus 11,000 meter. Get that. So if you pick up your calculator, plug those numbers in. You're going to get pressure at 20 kilometers, which is 5.483 times 10 to 3 Newton per meter square. Here we go, we got it. Next is the density. Density at the 20 kilometer altitude is rho 1, which is essentially this, exponential to the same thing, minus G0 RT H minus H1. So this is 0.36420 kilogram per cubic meter multiplied by exponential minus same thing, 9.8 meter per second square, 20,000 minus 11,000 meter, 287 joule per kilogram K, 216.66 Kelvin. Those are all standard units, okay? So it's just essentially the same thing. So this is going to give you 0.088 kilogram per cubic meters. Okay. One thing. I don't want to see you guys doing this, skipping the units. I'm just skipping the units here because everything is here the same. I want to see all units of all values in your equation. So even though after I've done this, I'm telling you right now, don't do this, please. If you do this in your exam, homework, quiz, what not to, I try to do this. Minus 1 point, show units. So I'm doing this simply because I'm showing here with all the units first. I'm repeating the same thing, that's why I'm skipping it. But please don't do this. This is not allowed for you. This is a luxury given only to me. So as a student, you shouldn't do this, period. But having said that, this is the end of Unit A2, and let's stop here.